How's it going? All right. Welcome back to another video series of Chem with Com. The topic today, for the next actually four video series or video lectures are going to be measurements, prefixes, and dimensional analysis, which just means conversions, basically. All right. So the specific topic for this video is units, measurements, and density. And those are the book chapters we'll cover. And just to give you back here, you could read through these in advance to get some background info before you watch the videos if you want. And remember, we have those accompanying questions for you to follow along with. All right. Units make numbers meaningful in chemistry and basically in life, right? So if we have the number one, don't even know what that means, right? One what? Well, if you put a unit after it or a unit with it, $1. Now it has meaning, right? A dollar, $1. You could buy stuff with it, right? Gram is a unit of mass. If we have grams, that's a unit. The number tells us how many grams there are. In this case, it's 1 gram. What about these decimals? What's 1.00 gram, right? What's the difference in having the 0.00, right? Well, let's say you jump on the scale, right, and you're 157, but you just get rid of all the decimals, right? 157 pounds. What if you're 157.9 pounds, right? If your scale can do more decimals, it's going to be more precise. The next time you jump on, it should read closer to the same, right? So yeah, the more decimals means more precision. And we're also going to have to go back and forth between different versions of these numbers, right? 1,350 grams is the same as 1.350 kilograms is the same as 1.350 times 10 to the third grams, right? You can see these are all some sort of grams, right? And you can see that these numbers look sort of the same, but there's decimals and all sorts of stuff, right? Well, kilo we know means 1,000 grams, right? So if we have 1.350 times 1,000, that's going to be 1,350 grams, right? We also know kilo means 10 to the third, right? Because of our previous lecture. And we did some background stuff on this, I believe, in the first topic, maybe. I think it was in the first topic. Yeah, some exponent stuff. So go back to the first topic if you want some background on this. Yeah. All right. So units in science are going to be using le Système International des Units, right? But standard international units, right? When we measure length, we're going to use meter, and the symbol is going to be lowercase m. Mass is how much, basically how much material there is, right? How many atoms, how much matter there are. That's going to be in kilograms. The symbol is lowercase k, lowercase g. Time is going to be in seconds, lowercase s. Temperature is usually Kelvin or Celsius. They're both kind of accepted. Kelvin's probably the standard, but Celsius is still used so much it's sort of there. We're not going to really use these. Electric current is ampere with a capital A. Luminous intensity, we're not going to really use much. It's in candelas, lowercase c, lowercase d. We are going to use this a lot in chemistry, and that's a mole. And remember, a mole is 6.022 times 10 to the 23rd anything, right? It's just a number of things, right? And the symbol is lowercase m, lowercase o, lowercase l. Volume we'll use a lot also, and that's the unit is name is liters, and it's a capital L. Now, I want to make something clear, right? There are something that's measured numbers where you take a device and measure it or calculate it through some other measurement, right? The last digit is an estimate or a kind of a guess, right? You're gonna, because if someone reads a ruler and you read a ruler, you might get slightly different readings, right? Because that last number is an estimate or a guess, right? And all those numbers are going to be significant when we do our calculations. There's also something called counted numbers, right? These are exact numbers. Um, and there's infinite amount of significant figures, right? So you don't include those numbers or the number of digits when you're calculating significant figures, right? Just like if you're counting the number of eggs in a little container, right? You can actually see the physical eggs, 1, 2, 3, 4, 5, 6, 7, 8, 10, and 12. Boom, right? That is going to be an exact number. But if you put those eggs on a scale and you say each egg weighs 5 grams, this we have 30 grams, 30.0 grams or 30.02 grams, right? If you weigh the eggs, those are a measured number, right? So you're going to have to be able to tell the difference between a measured number and counted number. All right. Length, distance. We included this just to see. We're kind of used to using yards and feet and inches, right? And so this is just a little slide that kind of gives you a scale of how big things are. Um, we're no longer going to use yards in here. We might use some stuff for conversions, but our standard unit of measurement is going to be meter. And then this is centimeter, right? It's the root unit of the base unit of length is meter. And this is what's called a prefix, and we'll get into those later. We have these equivalencies we'll talk about later, but this is an equivalency or a conversion rate. It has a number, a unit, an equal sign, a number, and a unit, just like this one, right? We could do either one. Let's just cap it off over here, but it has a number, a unit, which is meter, M for meter, an equal sign, another number, and another unit, right? So those are, we can use those as conversion rates or conversion factors, right? So again, length is like a distance and it's measured in meters. Mass, how much stuff there is, right? Our unit of measurement is going to be kilogram, lowercase k, lowercase g. They initially did this as a liter of water was going to be, boom, this is going to be the standard unit is 1 kilogram. Typically, you measure this on a balance or scale. Um, Weight is the force of gravity on mass. So weight equals mass on Earth because we did everything here. So we're using our gravity, right? But if you take something, let's say you take this brick and the mass is, let's say 2 kilograms, right? On Earth, right? That's going to be, the weight is 2 kilograms. Same thing, right? On the moon, right? Does that brick have the same amount of atoms in it on the moon? It does. But is it going to weigh less? Yep. Less than 2 kilograms, right? So mass is just how much matter or stuff there is in that object. And on Earth, mass and weight are the same. And it's usually, we're going to use a balance to measure that. All right. Time, just this is a weird philosophical thing, but the definition is the progression of his existence, which is kind of weird, right? Seconds and the unit is going to be, sorry, unit is seconds. The symbol is going to be lowercase s. Temperature, we just use thermometers to measure this. Temperature is average energy. Usually we use Kelvin. Every now and then we use Celsius, which is kind of a symbol like that. Um, we typically use the boiling point of water to figure out Celsius, and that was going to be 100 degrees boiling water, 0 degrees freezing water, and then everything else kind of came after that, right? Now we use Fahrenheit and Kelvin, and we'll learn how to bounce back and forth between these three different measurements, right? We're used to using Fahrenheit here, but we're going to now use Celsius. All right, moles. This is difficult-ish topic, right? In case that gets cut off, it's moles or mole, right? All right, mole is just a word that means a number, similar to how dozen means 12. Again, we covered this before, I believe, in chapter topic one, I believe. But you can reference the spreadsheet and see which chapter has what, right? And this is the actual number for moles. Like, so we say 12 equals a dozen. Well, this number here equals 1 mole, right? Just a number, right? The scientific notation or exponential notation version is this number. It's really hard to write this number, so we use scientific notation. Again, measured numbers, the last digit is an estimate or guess. All are significant. Counted numbers, these are exact numbers, and they use an infinite amount of sig figs. So if you are counting a mole of things, that's an exact number. But if you're measuring the amount of something in moles, that's a measured number, right? So depends on how you're measuring something. If you're measuring, there's the last digit is a guess and they're all significant. And you're counting something, they have infinite amount of significant figures. All right, volume. How much space something takes up. I'm just going to rewrite this here in case this gets cut off, right? Liters, L-I-T-E-R. The symbol is capital L. Liter is how much space something takes up, right? So mass was how much stuff there is, how much matter. Volume is how much space that matter occupies, right? So for instance, this is called a graduated cylinder. We could pour some liquid in there and you can see that it gets to a certain height and you read that number. And we'll go through this later, but this is 1 milliliter, really small amount, right? There's going to be some important equivalencies. So 1 cubic centimeter equals 1 milliliter, right? That's a very important conversion rate. Again, conversion rate, number, unit, equal sign, number, unit. Um, this CM3, that's kind of like a linear way to measure this, right? It's length times width times height. That's going to be 1 cubic centimeter. That equals 1 milliliter, right? And that'll let us convert from a volume in cubic centimeters to a volume in liters or milliliters, right? And this is 1,000 cubic centimeters equals 1 liter. We'll be using these a lot, so write these in your notes. Keep them very handy because it'll maybe get you out of some places where you think you're stuck. All right. All right. Length, distance, right? 1 meter equals 100 centimeters equals 1,000 millimeters, right? So 10 millimeters right here equals 1 centimeter. We'll learn how to convert back and forth to these. We actually already did in some previous chapters, so this is just kind of an extension of that. Again, we'll check the spreadsheet to see which lectures you can go back to. All right. All right, so length, a distance, right? More precise, the results are closer when measured the same way in case it gets cut off, right? All right. So more accurate means it's closer to the actual true measurement or value, right? So sometimes we don't know what that is, right? So we don't know if it's more accurate or not. But the definition of accuracy is close, more accurate is more closer to the true value or measurement. More precise, the results are closer when measured the same way. So let's take let's say you measure something with the ruler and it's 3 point, let's say 42 centimeters. And you take another ruler or you measure it a second time and it's also 3.42 centimeters. That means it's very precise because you measured those you took those two measurements and they were exactly the same, right? All right. Now let's analyze what's going on here. All right, we have two different rulers. One's going to be a centimeter ruler with no graduations between, or no kind of divisions between the large measurements, like 1 centimeter, 2 centimeter, 3 centimeter. The bottom ruler has more decimal, allows you to measure to more decimals, right? So let's look at this top one here. All right, so we're going to estimate this at, let's just say 3.4 centimeters, right? Because you can't really tell. It's not exactly like, I guess I'll get a different color pen, but if you look here, it splits this in half. It looks like about half, 3.5 centimeters. But it's a little bit below that. So I would call that something like 3.4 centimeters, right? Because again, this is sort of estimate. So we're not exactly sure what it is, but we know it's not 3. We know it's not 3.5, and we know it's below 3.5, right? So if it's below 3.5, we can't be 3.5. It has to be something below, so we just pick 3.4. But look what happens if you have a ruler with more lines in between of the measurements, right? So this is 0. This is going to be, if I can do this, 0 0.1, 0 0.2, 0 0.3, 0 0.4. This is 0 0.5. So every one of those is 0 0.1, right? Okay, so here, let's measure this. This is 0 0.1, 0 0.2, 0 0.3. Black line here is 0 0.4, right? If we were to split this up and put a line right there, right, that would be 0 0.5 centimeters, but it's not quite at 3.45, right? So it's below 3.45, so we pick 3.42, right? Another appropriate answer would be maybe 3.41 or 3.43 or 3.44. Those are all sort of, correct because we're estimating that last spot, but we know we have to report it to that last digit, right? To that second decimal because we can, right? We cannot do that here on this top ruler because there's not enough little lines or measurement marks to be able to say definitively this is 3.42 because this could have been 3.5 or 3.4, right? But we can't put that extra digit because we don't really know, right? Okay, so let's do another one. Let's look at this blue line now. This blue line falls exactly on that line. Or this one looks like it's exactly halfway. So we're going to call it 5.5 centimeters, right? But if you look at this bottom ruler, it also falls on that line. So it's 5.5, but since we know we can report this ruler to 2 decimal places, we have to report all measurements to 2 decimal places for that bottom ruler, right? So not all rulers, right? I'm saying this specific ruler with these specific markings on it can tell us it's 5.50 because we know this is not a guess, right? That's not a guess, right? Oops, sorry about that. But this is a guess or an estimate, right? Oops, let me erase that line because that gets a little confusing there. But this 0 is the estimate. Oh, estimate, right? The 0. Right? We know it's 5. We don't know if it's 51.49, right? So we're going to say that 0 is the guess, right? Because we know we can report it to 2 decimal places. All right. So the top ruler cannot be read to two decimal places because there aren't enough measurement marks. But the bottom ruler can be read to two decimal places. So all measurements must be to two decimal places. All right. It's a little tricky. We're going to practice this in lab to make sure you're getting this concept, but it's pretty tricky, right? Just even using a ruler in science. All right. Volume, how much space something takes up. Again, this is in liters, capital L. And this is the same issue where you really have to really learn how to read something properly. Again, these are the important equivalencies. Write those down in your notes somewhere. We'll use those a lot. We need to read from the bottom of the curve, which is called the meniscus, right? That's the bottom of the line, something like this. There's a lot of lines there. So, right, we want to read from the bottom of that curve. That's where the proper measurement is going to be. So again, this is a repeat picture, but I blew it up a little bit. So this is a graduated cylinder with all these little marks on it. It's filled out to a certain amount of volume of liquid. I blew this up. So if 21.5 is right in the middle of those two, and that red line is a little bit below, it can't be 21.5 because the red dashed line is a little bit below. So that could be 21.45. Or maybe that's 21.48 or 21.49 or 21.47, right? Or 21.44. These are all milliliters, all okay. Because everyone's going to read it slightly differently. Everyone has different vision. So they're going to read that a little differently. But since this can be reported to two decimal places, all measurements from this device must be reported with two decimal places. And it'll change. Sometimes the graduated cylinder won't have these little other marks. Like I think it skipped every other mark or something like that, right? So it's hard to say what every device you could read to because every device is a little different, right? So you're going to have to figure that on your own. And with practice, it'll get a lot easier. All right. So density, that's the next topic here. It's just pretty kind of brief, nothing crazy. It's mass divided by volume, and it's usually in grams per milliliter. All right, grams per milliliter. Again, I keep emphasizing this because we're going to use this a lot, but density equals mass over volume, right? We're going to use, for most stuff in this class, it's grams over milliliters or cubic centimeters. So grams per mil or grams per centimeter times centimeter, which is centimeters cubed. So these are the two different units we're going to use a lot of. There'll be other slightly different ones, but these are what we're going to use mostly. And it's mass divided by volume. Basically, it's how much stuff there is divided by the volume it's in. And we kind of know density, right? A piece of cloth or a piece of cotton is going to have low density, right? All right. This is going to be let's say steel or iron, high density, because the stuff is packed together. You can feel it, right? If you take a piece of steel, you can't really squish it, right? It's already squished as much as it can. It's packed together. So it has a lot of atoms in in a certain area, right? Let's say you take the same volume of cotton as you have steel, right? Cotton you could press and squish, right? So that's going to have less density, right? Because there's going to be less mass in the same amount of volume. All right, this is some common densities here. Um, Look at ice and look at water, actually. Look how the difference is. See, there's no water here on the right. Okay, so Water and ice have slightly different densities. So liquid water, solid water, right? Copper, um, look at copper and olive oil. So if you dropped a piece of copper and olive oil, right, the less dense stuff is going to be on top. So if you drop a piece of copper into olive oil, it should sink, right? We know it sinks because I mean maybe you don't, but usually most solids and liquids will sink mostly, not all of them, right? But if you look at the differences here, copper has a 9 gram per cubic centimeter. Olive oil has zero point 0.9, so it's almost 10 times the difference. So I'm assuming that if we took this piece of copper, dropped it into the olive oil, right, the copper would sink because of the difference in densities, right? 9 versus zero point 0.9, right? All right, let's do some work here. Let's learn how to do densities. To 3 decimal places, what is the volume of a cube with the edge length of 0.843? So let's figure that out. We're trying to go from 0.843 centimeters to centimeters cubed. There's a couple different ways you could approach this, right? We know that if we raise this to the third power, this will equal cubic centimeters, right? Another way to look at it is a cube, right? If this is 0.843 centimeters, this is 0.843 centimeters. And let's see, what's another one we have to do? This one here is 0.843 centimeters, right? We do all those together. 0.843 centimeters times 0.843 centimeters times 0.843 centimeters, right? That's going to be, I like to do units first because if you do the units and they work out, that means you did your numbers correctly, right? Centimeters times centimeters times centimeters, that equals centimeters cubed, right? And that's what we want. So let's do this. Now we're going to put in 0.843 times 0.843 times 0.843. So I'm going to hop over to a online calculator. Hopefully you can see this. So it's going to be 0.843 times 0.843 times 0.843. Enter. So I got 0.559, oh, sorry, 0.5991. Let's actually keep a couple digits. 0.599077. Hopefully I can remember that. I probably can already. 0.599. 077, right? How many numbers are we supposed to report? Well, we have 3 sig figs here, 3 sig figs here, and 3 sig figs here. Sorry, this is part A also. So this is going to be 3 sig figs. We cut it off here. So it's going to be 0.599 times 10 to the, oh, sorry. Nope. 0.599 centimeters cubed, right? So that's the answer for this part A. We just length times width times height, and they're all the same number because it's a cube. All the sides are the same. So it's going to be 0.599 cubic centimeters. All right. If the cube in part A is copper and the mass is 5.34 grams, what is the density of copper to 2 decimal places? Usually we don't tell you 2 decimal places or 3 decimal places. You have to figure it out from significant figures. And actually, let's can't cross this out and do it without the 2 decimal place knowledge, right? All right, here, what we're going to do is density equals mass over volume. All right, the mass they tell us is 5.34 grams of what's specific copper. All right, so now what we're going to do is we're going to do the volume. We calculated the volume before, right? We're going to use the one we didn't round, 0.077, and this is cubic centimeters of copper. All right, but we know we have three sig figs. So what we're going to do is put the over line over 9 to tell us that's how many sig figs we have. So here we have three sig figs. Here, even though there's 6 digits, we still only have three sig figs because of the previous calculation, right? We have that over line there. Let's do this. 5.34. So I'm going to clear this. 5.34, and it's right there, divided by 0.599077. Enter. So I got 8.9137. So let's look at that. 8.9137. That's 8.9137. And that's grams. The copper cancels out, and you get grams per cubic centimeter. All right. So if we want to do the proper sig figs, proper sig figs equals 3 sig figs. This is going to be cut off here, and it's going to be 8.91 grams per cubic centimeter. If we do what the book asks, we're going to do 2 sig figs, so that's going to be 8.9 grams per cubic centimeter. All right. Well, let's do one last thing to help you with the sorry. I want to do one last slide to help you with some problems on the quiz. So let's open up a new slide. Let's cut some stuff out here. Just so we can work on this together here. All right. All right. So let's say we're working with the same kind of stuff here. And I'm going to create a new question for this, right? So let's just cancel this out. So hold that. All right. So let me clean this up a bit too. Let's just cross this out. But we're not. Okay. So we have our density as, oh shoot, what have we calculated as? 8.91 grams per cubic centimeter, right? We'll say this is the density of copper. Let's say we knew we had let's see, we have, right, 4.53 grams of copper. How many cubic centimeters do we have? Well, I'm going to take our 4.53 grams. If you look up here, we have this density calculation, right? This allows us to convert from grams to cubic centimeters and then back to grams. Because of this, this is kind of like a conversion rate, right? All right, so what we're going to do is we're going to put the grams on the bottom and the cubic centimeters on top. So this is going to be 8.91 grams, and I'll tell you why, right? I'm just going to put some arrows so we can kind of keep track. And over here, since there's no number, it's going to be 1 cubic centimeter. All right. I flipped it, which you can do when you're converting, and we'll go through that in the next lecture, but this is how you're going to do this. The grams on top and the grams on bottom cancel out. So we're going to do 4.53 times 1 cubic centimeter over 8.91. So 4.53 divided by 8.91. Let's clear this. 4.53 divided by 8.91. I got 0.5084. 0.5, what was it? 084 cubic centimeters, right? There were 3 digits here, 3 sig figs, 3 sig figs. So I'm going to cut it off here. We have 0.508 cubic centimeters of copper, right? So we had 4.53 cubic centimeters. Sorry, 4.53 grams of copper. We're going to figure out how many cubic centimeters of copper we have. We're going to use that density as a conversion rate, right? Density, right? We're going to use that density of copper to calculate the cubic centimeters of copper. You can do the same thing if we have cubic centimeters, you can calculate the grams, right? So we can go back and forth because that is a conversion rate. All right, well, that's it for today. Thank you very much, and I'll catch you next time for the next video. All right, see ya.